Hello everyone, my name is Luke Hanks. This is my Lab 3 video for Physics 2211. So this is the black hole lab, and the purpose of this lab was just to explore how forces and momentum are broken up into their parallel and perpendicular components. We did that by simulating a star in a black hole system, and then we used the components to determine the mass of the black hole. So the principles I use here are Newton's universal law of gravitation, and then as you can see, I broke up the rate of change of momentum and the net force into their parallel and perpendicular components, which are defined over to the right. Here's my data. So as you can see, my three snapshots of my lab, they have the force vectors. The orange is the net force, which had a value of 8.47 times 10 to the 28th newtons. The purple one is the parallel component of the net force, which was 3.68 times 10 to the 27th newtons. And the perpendicular component was the light blue, which had a value of 8.46 times 10 to the 28th newtons. So my mass of my black hole ended up being 1.24 times 10 to the 34th newtons. Sorry, not newtons, kilograms. But the only source of error I can think of here is that the way the lab works is that it calculates the mass of the black hole for each time step. So the final mass that I received is actually the mass calculated at the final time step. And so it's not an average, which is what I could have done to make it more accurate, but I'm not really familiar enough with coding to know how to do that. So here's my coding. I changed the mass of the star to be 2.0 times 10 to the 30th kilograms, and I changed the delta T to be 86,400, which is the number of seconds in a day. Here's my coding. Second slide, I have changed the initial and final momentum to be the initial and final velocity times the mass of the star. Then I changed delta V and delta P to be V final minus V initial and P final minus P initial. And then dP dt is just delta P over delta T. The F net is dP dt, and then the P hat is P initial over the magnitude of P initial. And then d mag P dt is the magnitude of the final momentum minus the magnitude of the initial momentum all over delta T. So then I changed the parallel component of the dP dt to be p hat times d mag p dt. And I changed f net parallel to be dP dt parallel. And then I made dP dt perpendicular to be dP dt minus dP dt parallel. And the f net perpendicular is just dP dt perpendicular. So the mass of the black hole was just magnitude of the net force times the magnitude of the star's position squared all over g, which is the constant. The gravitational constant times the mass of the star, which is just a reworking of Newton's universal law of gravitation. And then finally here, I just have some aeroscale things. I changed the aeroscale to be 1 times 10 to the negative 17th. Changed the position for each of the arrows to be at the star's position. And then the axis for the first arrow was the F net times aeroscale. The axis for the second arrow was F net parallel times aeroscale. And the axis for the third was perpendicular times the aeroscale. So what does it mean? In my analysis, you should discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. So mathematically, these two are equivalent, but the difference is that net force is what's causing the change in motion, and the rate of change of momentum is what's resulting as a direct impact of the force. So basically, the force is what's causing it, and the change of momentum is the result of the force. All right, and so if you imagine the black hole is just replaced with another black hole in the same location, and then the motion of the star remains unchanged, and the only force is the gravitational force. Could you tell the difference, aka can you determine a different mass value? And the answer is no, because the motion of the star is determined completely by the force of gravity, and so if it remains unchanged, that means that the mass must remain the same for the black hole. And that is my lab. Thank you for listening.